Which?
Okay, so yeah, I was saying
Someone
yesterday,
points it out.
What are each of those?
this is, I think I left off, I was cut off in mid-sentence telling you why it's good to do some mental math. Yeah, that really is. So when you're doing, like, if it's high stakes stuff, I mean, yeah, you probably want to check on that. But if you're just doing math, in physics we call it kind of shirt sleeve math, where you're just really trying to scratch something out, it's good to try to do math mentally. Try to think about ways you can simplify seemingly complex arithmetic. The same kinds of neural pathways you use to do algebra are used when you do mental math. And so you simultaneously strengthen your algebra skills. Remember we were talking about how algebra makes you smarter. Algebra is it's a taxing thing to do on your brain, as you probably will attest to. It's mentally tiring. And so if you really use your brain in overdrive and you strengthen your brain, you strengthen the interconnectedness of your brain by doing math. Lots of crazy things. I told you about the eating with your offhand, right?
Yeah.
That's a weird one. Brushing your teeth, yeah.
I tried doing that.
Okay, so
I brush my teeth, my offhand is like slow.
My dad's
That's good.
Yeah,
I
it's
can't go in
it's
circles.
like-
Yeah, circles like this one's like.
Yeah, offhand is like nice and
When I
smooth.
start to go like fast, it's just going
He's
straight
also
back
very
and
picky.
forth.
Okay.
My example. Like he gets aggressive.
okay, so I think we had left off. We hadn't quite finished up our discussion, had we?
No.
We had a little bit further to go.
Yes.
And you guys are going to continue. You're going to continue kind of doing some preparing for some short discussions as you work on your next Moodle assignments.
In the computer lab right now.
Not right now, but
As we go
yes,
through
in the computer lab from time to time.
Yeah.
Okay, we were pretty close. Okay, we were 9 through 12, and okay, I think okay, I need everybody with me here. I think we had done up through 10, right? I think so.
Yeah.
Okay.
We can't see the screen if you're.
Oh, you can't see the screen at all.
Just have another 50
Okay. Let's see. Okay, so number 11, a car starts 2.0 times 10 to the 2 meters west of the town square and moves with a constant velocity of 15 meters per second toward the east. Choose a coordinate system in which the x-axis points east and the origin is at the town square. So first of all, let's write the equation that represents the motion of the car. So if this is essentially what I've done in front of the room now for quite a while, right? We're moving in east direction, pretend that's east, and it starts 2.0 times 10 to the 2 meters. Now how come they do that? There's a reason. It's still kind of annoying, but how come they write numbers using scientific notation there? No, although it has that benefit, doesn't it?
Accuracy.
Okay,
Accuracy.
it's telling us the number of sig figs, isn't it? Because if we write 2.0 times 10 to the 2, we know that there are 2 sig figs. If I wrote that as a non-scientific notation number, it would just be 200, right?
Yeah.
And the question then becomes, how many sig figs are there? Is it 1 or 2 or 3, right? And so there is a way around that, and that is to write using scientific notation. People don't do that very often because it just is kind of awkward to do, but it's a way you can deal with that. You can always specify the number of sig figs by writing a number in scientific notation. Okay, and we didn't need to with 15, right? That was clearly just 2. So how are we going to do this? What do we think? What are the things that we know here? And this leads into the stuff that we're going to talk about today. So this is the kinematics on steroids. We're gonna start doing
So
today.
it's
like
on the
this.
starting point of the constant slope.
Well,
Okay,
would it
good,
just
good, good. So if we were to graph this, it would look like a motion. Let's go that route. Let's graph this using a distance time or position time graph, right? So if we did that, we're gonna call this distance to the east, right? That's east direction, and this is time, right? And where do we start off? Okay, we start off west of the city center, so that's the negative east direction. So we start off down here at negative 200. And then it tells us, I went away from this, but what did it say? We go 15 meters per second, is that what it was?
Yeah, towards the east.
Towards the east, okay. So then what's it gonna look like from there? Okay, like this, right? Now, if I wanted to draw this accurately, I could use the slope, right? I know that, what is the slope gonna be? 15, right? If I wanted to maybe get, this is just kind of an unrelated point, but I'll just throw in a little math strategy for you. Whenever we want to graph a line or a line segment or array or anything like that, really all we need to do is get 2 points that anchor it, and then, like in this case, I'd start here and then travel through the point and extend. Where could I get another convenient point? X-intercept. Aha. Okay. How are we going to know where the x-intercept is? Okay, if we had an equation of motion, right, if we could use we don't have very many kinematics equations, but we've got one that would work here, don't we? We've got one that relates position to time, don't we? Remember what that one is?
D equals MT plus B.
D equals, we could write it this way, D equals D naught plus what? Another way of writing it is just displacement equals what? In terms of stuff that we would know.
Acceleration.
Okay, but what is there acceleration here?
No.
Acceleration is 0, isn't it? Because we're traveling at constant speed.
Final position minus initial position.
Okay, so final position minus initial position is displacement. That's true. What's that equal to? Remember? It's been too long.
Wait, isn't that?
We only really have one equation that does it.
Delta D isn't that D1 minus D0?
It is.
Delta D.
Yep. It is. So I'll tell you what, let's do. Let's write down the stuff that we know. What is D naught?
D starting position.
Yeah, and so what is that? Negative 200 meters, right? And we don't need to, we'll use standard units, of course. What else do we know about this? If we go back to the problem, and I guess I shouldn't have gotten rid of the problem. Let me take a picture of this. Okay, so there's what we got going on. Right? So what do we know? You told me the 200. What else do we know? Okay, what's that?
Average velocity.
Average velocity. There we go. Okay, so the average velocity is positive 15, right? Standard units, meters per second. Okay? And what are we trying to find? We want to write the equation that represents the motion of the car. Okay, so we want to write the equation that represents the motion, and really what we want to do is we want to be able to write what its position is going to be for any time. Does that make sense? So we'd like to do something like
You're saying like negative 200 plus 15.
yeah, something like that, exactly. So it's going to equal, my final position is going to equal what? Well, we've got a formula that says initial position plus what? Average velocity times time, okay. See what I'm saying? Now we can plug in a value for average velocity and initial position, and that gives us a model for it, gives us an equation, right? And we're gonna call this in physics, we'll call this an equation of motion. This is telling us about the motion of this object. So d of t equals negative 200 plus 15t. For any value of t that I choose, that's gonna give me back the corresponding position, great? Okay. So if I were to graph that, then, you already told me that it's gonna start right here at time 0. It has the initial value of the function is negative 200 and the slope is 15. If I wanted to know where that crossed the t-axis, so I could have another point to connect to, how could I use that equation to do it? Put in 0 for d, right? For the y, which in this case is d, my position. Because this is the t-axis, and that's where position equals 0, right? So if I set this guy equal to 0 and solve, what are the 2 steps in order to solve for t? We get a little algebra practice in here. Add 200. Good. Add 200 and then divide by 15, right? So we get t equals 200 over 15, which is what? 13 and 2/3? So it's roughly. So we're going to round to how many places go here? To 2, right? Okay. So that'd be 13.7, I guess. Oh yeah, 2 places. Yeah. Well, you're right. 14.
So is there a benefit, would you say, in the long term of looking at that as in the sense of dt and t instead of just thinking back to y plus b?
Oh, yeah.
Yeah, there is, because there's no difference except y equals mx plus b is it's completely abstract, and it doesn't really represent anything, but it does make sense for us when we're doing, and you're going to see this when we're doing lots of kinematics problems, which you're about to start doing. You want to be able to keep this stuff straight, right? And so yeah, things like putting in d for position makes sense, because then we know that variable goes with a specific type of quantity, right? And our independent variable is time. That's important to recognize. In almost every physical situation, when we're doing physics stuff, our independent variable is usually t. Because aren't we mostly interested in watching how things change with time? I mean, it's pretty boring to look at the physics, and it's not boring, but there is a physics of things that aren't moving, and that's called statics. Like if you're looking at a bridge, for example, building a bridge. Well, the bridge isn't really going to be moving; it's just going to sit there. But we still have to do some physics to make sure that we can support all the proper loads. But when things are moving, which is what we're going to focus more on throughout the year, we want to know what's happening with time. Think in terms of a movie. Like at some point in the fairly near future, we'll look at things like, what if we were to, shoot a bullet out of a gun at an angle and it had a certain velocity when it left the gun, then where's it going to land, or how high is it going to go, or something like that. So we've got to move this model forward in time to figure out to answer our question, right? So t is our independent variable. Okay. All right, so we got the equation. Where will the car be 10 minutes later? What can I do? What do I plug in?
Because, yeah, it's only on the second.
Okay, so what I have to do? I have to convert it to seconds, right? So 10 minutes, I have to multiply by 60, so I get 600 seconds later, right? If I want to find out where it's going to be, and I just plug that into my equation. And when will the car reach the town? Well, actually, we just answered that, didn't we? Yeah, about 14 seconds is when it gets up in here. So along this axis, we'd be at about 14-ish when it crosses through.
Making good time.
Yeah.
Yeah,
That's solid.
Yeah, good teacher school. Teachers. Okay. All right, so last question. Okay, going back to the same situation we were just at. If a truck was 400 meters east of the town square moving west at a constant velocity, so let me put this up here. Okay, let's look at this two different ways. Let's look at this in terms of a graph and in terms of an equation. How about? Okay, graphically, we already drew the graph of the car, right? The graph of the car looked like this. Agreed? So that's the car. What about the truck? The truck started off 400 meters east of the town square, so where's that going to be? That's going to be above, further. Like I said, this isn't drawn to scale, all right? So that's 400, and it's going to move to the west at a constant velocity of 12.
I don't get why
12.
you say on the x-axis point east.
That's just saying that east is representing the positive direction of the problem. Okay. So we're saying, so in other words, I'm sorry, that's not east, this is east.
Yeah.
Sorry. Yeah, there we go.
Silly.
This is T, right? So this is the positive direction. So the car is actually moving in the positive direction, but the truck is starting east of town square and moving to the west. So its position is going to tend to get more negative, right? Its velocity then would be what? If it's moving west at 12. Negative 12, right? Okay, so isn't it just going to, it's going to look something kind of like this then, isn't it? Right? What's the significance of, notice that little touch, you probably noticed that.
Yeah.
Yeah, there you go.
I got you.
So what's the significance of the purple point?
When they cross that.
Okay, yeah. Now, it's where they cross paths, but it's also when they cross paths, right? That's going to be the position and time when they're in the same, hopefully not exactly the same place. Maybe go by each other, right? Okay, so we want to know then, here's the graph, but what if we want to find the time and the place where they pass each other? What am I going to have to do?
You have to find the.
How am I going to do that? The graph, it gives us a pretty good conceptual idea that.
Oh,
Busy.
Oh,
I wish.
plug in zero for her, plug in zero for time, zero for cut, that coordinate, whatever it is for. Just set them up. For time and.
Right, so.
Into your equation.
Right, so the coordinates of this, let's just say hypothetically that the coordinates of that point were at, I don't know, say they were at 15, 150. What's that telling us?
That's where they.
Well, there's a really.
15 seconds and then at 100.
Okay, they would pass by each other after 15 seconds, and they would be, in this case, 150 meters east of the town square. Now, that's not the right answer, probably,
Right.
right? But we've got to find the right answer now. So how are we going to do that? This is really, I think this is a really good thing to look at, because this is where, here you've spent a lot of time throughout your math careers learning how to solve mathematical problems. And I think that's entirely appropriate that you focus on math and not really try to make it too story problem-ish. I really believe that. I think it's, you got to learn math well, and then eventually you can kind of start to apply it. But here's a place where we can start to make a connection, right? You've done stuff like this a lot. If we find the intersection of those two lines, really all that is we're just solving a system of two linear equations, right? In this case, that intersection represents something important, though. It is the physical answer to our question. Yes, ma'am. So, go ahead. No, you're right. You got it. No?
Or are
Okay.
we trying to figure out how we can?
So we've got, how about if we do this then? We'll say the position of the car.
Yeah, do we find,
You already told me this, right? It's negative 200 plus 15t, right? Okay, what's the position of the truck?
400?
Okay, negative or positive? Positive. Ah, good. Minus 12t. Good.
No, minus
Ooh. Okay, right? Yeah, so we could. Now, but let's think about, I want you to, you're exactly right, and probably your intuition tells you gotta just maybe substitute here, but I want you to think why. Think about, make the connection to the physics of this.
Oh, because they have to equal the same.
Ah, okay, good, because by setting these equal to each other, really, we're just asking the physics gods, when are they at the same place, right? We're saying, when are their positions equal, right? By setting them equal, agreed? Okay, so then we end up with 400 minus 12t equals negative 200 plus 15t, right? Okay, how many variables are there in that equation? One, so I can solve for it, right? What am I gonna do? I'm gonna push the t's to the right, agreed?
Yeah.
And the numbers to the left. So I'm gonna get 600 equals 27t. Everybody agree? Yeah. Divide by 27. And we're gonna get 22.2 repeating, okay?
How did you do that in your head? Mental math. Nice mental math.
22.2 repeating, okay, so now keep that on your calculator though, because we don't wanna accumulate rounding here. So if I wanna go back and figure out, that's part of it, right? We know that they're gonna pass by each other after exactly that much time. Okay. We'll have to, of course, round our answer because these were measurements. But if we want to know where's the position going to be where they pass by each other, what do I do?
You plug it into either.
Which one do I plug it into?
Into the car.
How come either one works?
Because
if they equal.
Yeah, they're the same distance, right? That's the whole premise of the situation here. So we'll plug it into the easy, well, they're both pretty easy. So we plug it into probably
That one, the top.
this guy, yeah.
I want to do the bottom.
So that's gonna give us 26, or 24.4 repeating, no, I'm sorry, what am I saying? It's gonna be,
That's heavy mental math. That is heavy.
what's gonna be, it's gonna be 23.3 repeating, isn't it?
You know what?
230, sorry, it's gonna be 233.3 repeating, right? 130.
How do you do that?
Okay.
How do you do that? Wizard.
Mental math.
Wizard.
You watch all those mental math videos on Facebook that teach you how to do stuff like that.
So 133.3 repeating, right?
Literally don't know how to do that.
Okay.
After you agree.
And so we'd have to round both those back, but that gives us our answer, right?
I've watched them too, I
Okay.
just don't remember.
Oh, yeah, it's just like, no, that's cool. Yeah,
All right.
Can't wait to not use that. Yep.
Okay, so you guys will just, you know the criteria, you gotta get on Moodle and give yourself a grade on that assignment. So the next thing I wanna do, now we're gonna move into real kinematics. So we're gonna make our complete list of kinematics equations that we get to use. We've already got one. We already know that, that displacement equals v bar times t, right? Or if we want to write that maybe in our other way, we could say, in terms of position, which I actually like better, position equals initial position plus average velocity times time. Okay, we have another one too. We actually know that because of the definition of velocity, we did this one before, remember, acceleration equals change in velocity over change in time, right? So if that's true, we could calculate our final velocity, couldn't we? Right? Because if we solve for delta V just equals a t, right? Delta t is just t, right? Right? all I did is multiply each side through by delta t, which is the same thing as t. We'll just call it a t. Get rid of the delta. And then that just gives us v final minus v initial equals at, right? Okay, and so if I just add the v naught to the other side, we end up with final velocity equals initial velocity plus acceleration times time. Well, doesn't that look, hopefully that's starting to make a little more, that symmetry makes a little more sense. Said this before, but I'll reinforce it again. Velocity is to acceleration as position is to velocity. Look, those equations are the same if I just trade the d's for v's and the v's for a's, right? Okay, and that makes sense because velocity is the slope of a position time graph, but acceleration, remember, is the slope of a what? Velocity time graph.
Is there if you were able to create a third function that followed that same rules, would whatever be that is the v to the a, whatever
It
the
is.
a's,
And that's
would that be
called
the
the
fourth
jerk,
dimension?
actually.
Would that be like the fourth dimension?
No.
Fourth dimension is like the
Are these all like separate with time?
Say it again.
Are these all separate?
anti-time.
Oh, no, this is just what I used to get that. I'll erase all this garbage, right? So that's the equation we get, okay?
Wait, so what would that be? What's the third one?
What do you mean? It's called the jerk.
What it,
The jerk is the rate of change of acceleration, but we never use it because it's.
I feel like
Okay, so there's our first two, depending how you want to write them. I gave you another one. Remember, I let you use it on one of the problems in the last problem set. You remember what that one was?
Delta G equals V naught and T equals
Okay, good.
average acceleration times T squared.
Okay, so displacement we can also get in terms of acceleration and initial velocity. We could write it as initial velocity times time plus 1/2 a t squared.
Average, right?
Say it again.
Average in,
Average acceleration.
yeah.
Yeah. And for us, we can put that if we want to. For us, acceleration is going to be constant all the time anyway. So that'll be.
why will it not be constant? Like how far to the year?
And when you take calculus basically in college.
Oh,
Yeah. So we could write that over here as position equals, if I just write that as d minus d naught and add the d naught to the other side. Okay, and then there's one more. Now I want you to notice, all of these are vector issues, right? Okay. There's one more that we get that's kind of a cool one. This one, and all of these, what's the independent variable for all of those equations of motion? T, okay. Now look at this one. How about that?
Yeah. Where's the time?
There's no time.
Time
So
doesn't
that's
exist
really
anymore.
can be a pretty handy one, because if you don't know any information about time, this is one that you can take advantage of. That
Is that a square?
It's a squared.
So
Yeah. That's that's a vector hat right there. I'll give you a handout. In fact, I'll put it on Moodle, so when you're doing the assignment, you can just open it up in like a PDF or something right next to it with these equations of motion on it. Kinematics equations. So that's the list that we've got. Okay. Really, we already knew kind of 3 of those, but this is the one that's a little bit new to us. So I'm going to give you a series of, I don't know, probably break them into small pieces. So some short problem sets where you got to do some kind of real, fairly challenging kinematics problems. And these are kind of fun. You get to answer. I like this. You get to answer questions about something. You make a real prediction about something. So the way that you got to do these though is real similar to the way that we started with those introductory ones we did a while back. You always want to, first thing you want to do is probably what when you're given like a physics problem, kinematics problem. What do you want to do?
Identify your.
You gotta read it very carefully.
Identify
Read it
what you
twice.
have.
Identify what you have. Good. You want to interpret the problem in terms of the values of these kinematic quantities, right? And then once you know what you have, and probably also what else you probably want to know, what you have and maybe what you're trying to find. you wanna find the equation, hopefully the single equation that's gonna get you there. But it might turn out that maybe you even need to do, in some cases, more than one, right? You might have to use one of these equations to calculate a different quantity, and then go back and use a second one or something, right? You just kinda get good at that. So this is what you're armed with. Now let's take a look at a problem or two. I'm just gonna take a couple out of the book.
Yeah, no. Yeah. Now we're qualified for this class.
You're right.
But by the time I looked up, you had the net set.
Okay.
No, Scott, you said
Ooh, toy train. We should do that one.
Okay, let's do number 19.
That's not a good idea. You don't wanna coast backwards down.
No, that's not a real good idea.
you're out of gas.
Unless you got a bump starter.
Yeah, I would kinda want to.
I
would rather coast forward down, hell yeah.
That'd be fun in reverse, more fun in reverse.
Okay, what do we got here?
Backwards.
So here's, everybody take, if you don't have your notebooks out, take your notebooks out. I'd like you to read this, and I want you to think about this problem a little bit. I want you to think about what our strategy is gonna be. Okay? Okay, car is coasting backwards downhill. Driver starts the engine, puts on the gas evidently, and starts to move. After 2.5 seconds, the car is moving uphill at 4.5 meters per second. Assuming that the uphill is the positive direction, what is the car's average acceleration? So we'll just assume it's constant acceleration. So you gotta come up with, what's the first thing you wanna try to find?
So what,
We wanna find the acceleration from the 3 meters a second backwards to.
Okay, well, so A is what you're looking for, acceleration, but then you have to be able to identify some other stuff.
isn't it
You have to know the average velocity.
Okay. You gotta know you have to know some other things, don't you? You have to be able to extract the kinematic quantities from that situation. So somebody tell me, what's one thing we know?
initial speed?
Oh, okay, what's the initial speed?
-3.
-3, right? It's rolling down the hill. We said up was positive. So this is telling us right here, let's see, this guy right here, that's telling us that V naught equals -3.0, standard units, right? What else do we know?
You know, time.
Okay, we know time. Yeah, we know how long the movie runs, don't we? The movie runs for how long? 2.5 seconds. Okay, so T equals 2.5 standard units.
How many moments is that? You know, final velocity?
Okay, we know final velocity. So we know V final equals positive 4.5. And what is it that we're trying to find?
Acceleration.
Acceleration. Oops.
Would it be 8.5?
Well, before we jump to there, what's going to be the equation we're going to want to use?
That one right there.
Velocity equals acceleration.
Okay, right here, right?
Yeah, that's
Okay.
what I was.
So that's the one we want because that's the one that involves all the stuff that we're given and what we're trying to find. Okay, so now here's where you got a fork in the road. You could either, we're trying to solve for acceleration, so you could either plug the numbers in now and solve for A. My preference is always to solve for the variable. So we're gonna start with this equation, and let's isolate A in that equation. So what do we get when we isolate A in that equation? What are the two steps in order to get the A by
And
itself?
delta V over T.
Okay, I'm gonna subtract
So A, B,
V
V
naught.
naught.
and then divide by T, right? Okay, so we could rewrite that as A equals V minus V naught over T, and now all I've gotta do is plug and shove, right? So we plug in, our final velocity is 4.5 minus our initial velocity of -3.0, right? All divided by 2.5. And you should put all that into your calculator at once and get an answer, which is gonna be 3, right? 3.0, is that right? 3.0, what are the units gonna be? Meters per second
Square.
squared.
Acceleration.
Meters per second.
Okay, make sense? We not done? What are we out here?
2 more minutes.
10? We'll cut her off.
For a moment.